Hi everyone, welcome to today's webinar. This webinar is a presentation of Clean Energy Group's Resilient Power Project and the Northeast Electrochemical Energy Storage Cluster, also known as NESC. And our topic today is fuel cells for wastewater treatment plants, and we have several excellent guest speakers joining us today for this webinar. And before we get started, I'd like to go over just a few quick housekeeping notes. All of our participants today are in listen-only mode. That means that you can hopefully hear us, but we cannot hear you. So you have a couple of options for joining the audio portion of this webinar. You can use your computer mic and speakers, or you can call in using a telephone. And if you do, we ask that you please enter the PIN number that you will be given into your telephone keypad. A very important request, please submit your questions as you think of them throughout the webinar by typing them into the question box in your webinar console and hitting send. We will be reading through your questions throughout the webinar, and we will be saving time for a Q&A at the end of all of our presentations. We will be answering as many questions as we can. So again, just to make sure that your question does get answered, type it in as you think of it. And a final note, this webinar is being recorded, and you will find a recording of this webinar as well as a copy of webinar slides and all of our previous webinars for the Resilient Power Project on our website at the web addresses that you see on your screen. And with that, I'd like to pass it over to our host today, Seth Mullendorf. Seth is a project manager here at Clean Energy Group.
Thank you, Samantha. So I'm just going to give you a brief introduction to who we all are here. So this is being brought to you today as a joint collaboration between Clean Energy Group's Resilient Power Project and the Northeast Electrochemical Energy Storage Cluster. Clean Energy Group is a national nonprofit that works to advance clean energy technologies through finance initiatives, advancing technologies, policy, and getting projects done. We're supported by a number of foundations. The Resilient Power Project in particular is supported by the JPB Foundation, Kresge Foundation, and Certain Foundation, and we're working on that along with the Meridian Institute. We also have a sister organization, the Clean Energy States Alliance, which is an organization of state energy policy leaders who manage state energy funds. So if we could go to the next. So a little bit about the Resilient Power Project. Resilient Power Project was created in the wake of Hurricane Sandy as an answer to the question of, is there a better way to provide power for vulnerable communities during power outages in the wake of things like natural disasters, as opposed to diesel generators, which tend to have a rather high failure rate and some other issues. So through that project, we are increasing awareness both at the public and private level by getting out reports and doing webinars like this one about resilient power. We're also engaging officials at the city level as well as state and federal level to advance programs that support resilient power and policies. The project itself has a focus on low-income and other vulnerable communities, such as the elderly and disabled, and the critical facilities that help support them. In addition to advocating for these projects and getting information out there, we also have some technical assistance for the pre-development of projects to help get them going and do the initial scoping of projects for developers. So this is our website URL here, the resilient-power.org. On that, we have a number of reports and newsletters and webinar recordings, including this one will be posted shortly after we are done here, probably in the next couple of days. All right, next. I also want to mention this is brought to you by both Clean Energy Group and the Northeast Electrochemical Energy Storage Cluster, also known as NESC. NESC is a network of industry, academic, government, and non-government leaders that are working to support the development, production, promotion, and deployment of advanced fuel cell technologies for energy storage solutions. Of course, NESC is focused on a cluster active in the northeastern part of the country. So now I would like to introduce you to our speakers for today. So our talk is going to be on fuel cells for wastewater treatment plants, and we have some great speakers today. First up will be Ken Wicker, and he is the Director of Business Development for Fuel Cell Energy. Ken has 20 years of experience in energy efficiency and renewable energy technologies with a wide range of domestic and international sales experience. He is a former Peace Corps volunteer where he managed rural electrification in the outer islands of Tonga. Ken has an undergraduate degree in environmental studies from the University of Kansas, a certificate in energy management from California State University at Sonoma, and a master's degree in energy policy from the University of Delaware. Next up will be Jim Mullins. He is a senior engineer at the Orange County Sanitation District in the Operations and Maintenance Division. Jim has a BSEE from Cal State Long Beach and is a registered electrical engineer in California. He has been with the Orange County Sanitation District for 20 years now, and presently his responsibilities within operations and maintenance include energy reduction and optimization, as well as staff support for electrical maintenance and energy issues. We also have Ernest P. Marquez Jr. with us, and he's a principal engineer with the city of Riverside, California, and he has a civil engineering degree from California State Polytechnic University in Sonoma, and registered as a civil engineer with the state of California. Ernest has over 25 years experience in wastewater industry, and currently for the city of Riverside, he is the principal engineer for the Public Works Department Sewer Division at the Water Quality Control Plant. So with that, I'm going to hand things over to Ken, and we will follow the presentation today by some question and answers. So as Sam said, please don't hesitate to put in some questions now, and we'll get to everyone that we can. Okay, Ken?
So the agenda for today is to go through the opportunity at wastewater treatment plants, talk a little bit about fuel cell energy's technology, go through some case studies. We're going to talk about renewable hydrogen, and then we're going to talk about the economic opportunities. So the opportunity at wastewater treatment plants is that, at Fuel Cell Energy, we make a multi-megawatt carbonate fuel cell, and that's well suited for large wastewater treatment plants because wastewater treatment plants are generating a lot of on-site biogas. That biogas is often greater than about 60% methane, which is a perfect source for our molten carbonate fuel cells. We don't need to have pipeline natural gas. We have our own fuel cleanup skid that can get out any of the siloxanes or sulfur or any of the types of things that might harm the fuel cell stack. So wastewater treatment plants with their biodigesters are a good source of biogas. And because that's considered a renewable resource, we can garnish all the benefits associated with treatment, with running a treatment plant on renewables. And then also, wastewater treatment plants operate 24/7, and fuel cells do as well. We like to run our fuel cells we consider them base load operation, and because of that, they like to get up to speed and run at full output, which is either 1.4 or 2.8 megawatts, 24/7, 365. And so because wastewater treatment plants are using electricity 24/7, 365, there's a good fit between the energy producer and the energy consumer. So Fuel Cell Energy is an integrated fuel cell company. We're based in Danbury, Connecticut, where we do all of our research and development, and we have a manufacturing plant in Torrington, Connecticut. And then we have sales teams in North America, primarily the East Coast and the West Coast, because that's where electricity prices are the highest and where fuel cells will provide the most value. And then we also have partners in Asia and Europe that sell our fuel cells. Now, behind the sales team is a project finance, which I'll talk about later, a construction management team, and a service team. And so whenever anybody, installs one of our fuel cells, they're dealing with fuel cell energy employees who will not only help finance the thing, but build and maintain it as well. At our headquarters in Danbury, Connecticut, we have a network operations center that's staffed 24/7, 365, and is monitoring every one of the fuel cells that we have operating worldwide. So if there's ever a fuel cell tripping offline from a utility disturbance or whatever the case may be, we can either fix it remotely, or we can contact one of our service technicians that we have deployed around the world to go in and address the issue. So as I mentioned, we make these things in 1.4 and 2.8 megawatt sizes, and the guy you see on the left is holding an individual fuel cell, and on that fuel cell you've got an anode, a cathode, and a carbonate layer that basically looks like porcelain. And what's going on inside that fuel cell is that you're introducing methane, which is CH4, and air, which is the oxygen in the air, and the CH4 is migrating to the oxygen to create CO2 and H2O, electricity, and heat. And so what we're doing is we're just harnessing that electricity and that heat and selling it to the end user. And so when you put a bunch of fuel cells together, you get a fuel cell stack. In our case, it's a 350 kilowatt fuel cell stack, and you put 4 of those stacks together and you have a 1.4 megawatt module. And then you put 2 of those modules, those 1.4 megawatt modules together, and you have a 2.8 megawatt plant. And you can put as many 2.8 megawatt plants together as you want. The largest one in the world is a 59 megawatt fuel cell park in South Korea, and the largest one in the United States is a 15 megawatt fuel cell park in Bridgeport, Connecticut. Next slide, please. So why fuel cells? Well, they're clean, quiet, and efficient. Because fuel cells are not burning any kind of fuel, they're electrochemically processing it. You're not burning it, and so you don't have the same sounds that an engine would have. You don't have the revving sounds. You don't have any of that. What you do have is a sound from a blower blowing the fuel into the fuel cell stack, but beyond that, they're very, very quiet. There's an energy cost savings component. And I'll talk more about the PPA and the finance and the lease later on. But what we'll do is we'll take a look at what you are paying now for utility power, how much you're paying for gas, and then we'll run the economics and hopefully provide you with the savings. And so we primarily sell these things in New York, New Jersey, Connecticut, and California, because those are the places where the cost for electricity is high enough that we can provide substantial savings. And then we do finance these things, so there's a low risk. We'll offer a PPA option that is incorporating the cost of our installation and service, and offer it to the end user on a power purchase agreement. We have a highly reliable fleet that has an enhanced resiliency. It's running at about 95%. And then you can see in the table right there that our efficiencies are quite high, and our production of NOx, SOx, and particulate matter is quite low. And then the carbon dioxide is also lower than you would get from the grid or from a regular fossil fuel plant. Next slide, please. So this slide talks about efficiency and its heating value, right? And so on a 2.8 megawatt fuel cell, it's about 47% electrically efficient. And when you utilize the waste heat, either hot water, steam, or absorption cooling, so we can create any one of those three options, it increases the efficiency up to the mid-60s. And because our fuel cells are running at about 1100 degrees Fahrenheit, they've got an exhaust of about 700 degrees Fahrenheit, then they can make a fair bit of hot water steam or utilize the heat for absorption cooling. And then if you use a secondary heat exchanger, then you have a need for hot water, say at 60 to 90 degrees Fahrenheit, you can bring that efficiency up even higher. Next slide, please. So our fuel cell, the 2.8 megawatt fuel cell, fits into an area about the size of a tennis court. And that gray area that you see shaded on the right is just for construction and crane access, and of course that goes away afterwards, and you can return that to whatever it was before, a parking lot or a loading dock or whatever. But you can see the outline of what a fuel cell would look like from overhead, and like I said, it's about the size of a tennis court. So each one of those 2.8 megawatt fuel cells generates about 22 million kilowatt hours annually and about 4.4 million BTUs per hour of waste heat that can be used for, as I said, either hot water, steam, or absorption cooling. And then that table down below there gives you an idea of how efficient the unit is, depending on what you're doing with the waste heat. We replace the fuel cell stacks about once every 5 to 7 years, and you know, when we install a fuel cell, it's going to decrease in electrical efficiency and increase in waste heat efficiency over the course of that stack's lifetime. And so that's why you see the difference in the two middle columns between the beginning of life and the end of life. That's what DOL and EOL stand for. So a little bit about the fuel requirements. We need an output of about 55% methane. The CO2 doesn't need to be removed. We can dilute the compositions without derating the fuel cell, and so what we do is we put in our own fuel cell skid that we build and maintain and manage, so we know what's going into the fuel cell, and that makes a huge difference in making sure these things stay up and running. You know, for a population of about 400,000, we can put in a 1.4 megawatt fuel cell, and for a population of about 800,000, we can put in a 2.8 megawatt fuel cell. And so, you know, if you've got a population of say 1.6 million, then about 2.8 megawatt units, or 5.6 megawatts, would be the size that we would recommend to put in there. And then, you know, you can see below what we need on the fuel quality. And like I said, we put in our own fuel cleanup skid to make sure that we're attaining that. So we've got one of these fuel cells. We've got 1.4 megawatt fuel cell deployed at Central Connecticut State University. It's a combined heat and power plant. It's on the campus there in New Britain, and supplies about 1/3 of the campus needs. If you're interested in going to take a look at it, I can set that up for you with some of my colleagues back in Connecticut. The efficiency drives very favorable economics for them, and you can see what President Jack Miller had to say about it in his review of the fuel cell plant. They also have a microgrid associated with this fuel cell, and that has proven, you know, quite reliable for them, and has helped them meet their clean emission goals. I'm going to talk a little bit more about microgrids when it comes to discussing the incentives at various states. The state of New York has an incentive for microgrids, and so I'll talk more about that. And then here in California, we've got a directed biogas project going on at the University of California, San Diego. I've been to that fuel cell many times. It's a 2.8 megawatt unit, and it's driving a 400-ton absorption chiller in addition to the 2.8 megawatts of electricity. It's really helped that particular university reduced their carbon goals. The Janet Napolitano, the president of the UC system out here, has passed a mandate that all the UCs need to get their carbon down by 2025, and so UCSD in particular is well on the way to attaining that, partially because of the 2.8 megawatt fuel cell that they've got installed, and then they've also got some energy storage and some cogeneration projects as well as solar going on that helps them reduce their emissions. But anyhow, that fuel cell operates at about 68% efficiency. It's been in operation since 2012 and utilizes directed biogas from the Point Loma wastewater treatment plant. Next slide, please. So this is the city of Riverside. I'm going to turn it over to Ernie Marquez for his comments on the city of Riverside's wastewater treatment plant and their 1.4 megawatt fuel cell.
Thank you very much, Ken. Here in Riverside, we're undergoing a $200 million plant expansion, and right now we treat up to about 30 million gallons per day, and we're going to be going up to, at build-out, 52 million gallons per day. Fuel Cell did approach us in the beginning on their 2.8 fuel cell. However, what we did is we looked at, okay, can we supply the digester gas to them, and we thought, okay, let's start out with a 1.4 first, and we know we can supply that gas to them. So, and that's what we went with. Our benefits: we have a renewable baseload power, solves our waste disposal problem, and provides continuous clean power. We wanted to make sure that we used the biogas instead of just flaring it off. Due to the fact, we want to stay clean. Now, Fuel Cell, they have designed the system. They will manage and operate the biogas cleanup skid. The ultra clean power facilitates clean air permitting. Distributed generation enhances power reliability and energy security. High efficiency drives economics. Here in Riverside, we do have the city does have its own, we want to call it power utility. We buy, power from them. With all our new systems that are going to be coming online, we're kind of like, I want to call it hedging our bets here to have a cheap, reliable power for us here at the plant. And hopefully, we have a construction of the facility will be in early April, and we're all excited here about that. And I think that should be it for our plant. And back to you, Ken.
Yeah, that's back to me. We have Jim Mullins coming up next. He's going to talk to you about the Orange County Sanitation District in Fountain Valley, California. And they had a tri-generation fuel cell. He's going to speak to you a little bit about that. Go ahead, Jim.
Okay. I will just say what the district's experience has been with the 350 kW single stack fuel cell. They operated it for 3 years, from 2011 to 2014. It is now mothballed. Some of the problems that we encountered included our plant power interface with it and some other components that had to be replaced or repaired. The main lesson we learned from the operation of it was the need to have it base loaded. As had been stated before, you can't really be ramping the fuel cell up and down or have interruptions. It tends to decrease the life of the stack. And there was no ballast resistor on this installation that it could have been switched over to keep it loaded. And so there was some uncontrolled interruptions there that reduced the life. So I think in future it's best to at least for our needs, we would have needed something to prevent the interruptions from impacting the life of the cell. Okay, on the proposed trigeneration system, this facility could be located where the existing fuel cell is located at Plant 1. There is some significant site work required in order to locate it there. The last proposal discussions, as far as I am aware, occurred back in March, and so that proposal is still under consideration now 6 months later. And so I don't know that there is anything else to really discuss.
Okay, thanks, Jim. So then moving on to the next slide, you know, it's about halfway down through this slide and picking up on that. You know, that, as I mentioned, the fuel cleanup skid is all in-house. We offer a 15 to 20 year maintenance and service contract that goes along with the fuel cell, and we've got a whole maintenance program that goes along with that. And so, you know, about once every 18 months or so, we need to come in and shut the fuel cell down for a couple days and replace some pumps and put in some new filters and whatnot. And then about once every 5 years, you know, depending on how clean the gas has been going into the fuel cell, we will take the stack out and replace it with a brand new stack. And of course, on a power purchase agreement, that's all incorporated into the price of the fuel cell, and we will pay for that, you know, out of the PPA, the price per kilowatt hour. And that's about it. Other than that, these things, as Jim alluded to, like to run 24/7, 365. They're not designed to cycle up and down. They like to just get up to full speed and keep running at that speed. The way I liken it is to compare it to you know, when you get on and off the highway with a normal car, you know, you're able to accelerate up to 65 or 70 miles an hour, and then when you get off your exit, you decelerate. And what fuel cells like to do is they like to just get on that highway and run 24/7, 365. So let's move on to the next slide, project finance options. Fuel Cell Energy has an agreement with NRG, one of the largest independent power producers in the country. They gave us $40 million in July of 2014 to help fund fuel cell projects. And so we have money available on a PPA that a private entity, either NRG or some other financing organization, will come in and build this fuel cell plant, and then we'll turn around and utilize a power purchase agreement structure where we charge a price per kilowatt hour that is ideally below what you're paying now for electricity, and then you get the waste heat as an added benefit to that. We also can lease these things. And the advantage of the PPA over the lease is that if you are going to you know, get into a PPA situation, then you're bringing somebody else in as the financier, and of course they're putting up the money to put this thing in, and so they're going to want to get their money back, right? And so what they do is they charge you per kilowatt hour, and if the fuel cell's not running, then you're not charged, right? And so for that week, every 5 years when we replace the stack, if it's not producing electricity, you're not going to be charged for that. And so, you know, the benefit to the end user is that there's no risk, right? If we don't come in and spend millions of dollars putting in this fuel cell, and we guarantee you that it's going to give you 22 million kilowatt hours a year, and if for some reason it only gives you 21.5 million kilowatt hours per year, you're only paying for 21.5 million kilowatt hours per year. And then on the lease, you know, the disadvantage of the lease obviously is that if the fuel cell's not running, just like when you lease a vehicle, you're still paying for that lease. And then obviously we offer purchases as well. Next slide, please. So in the United States, we have incentives in place. Here in California, it's called the California Self-Generation Incentive Program, and it currently pays about $1,650 per kilowatt for the first megawatt, and then an additional $1.46 per kilowatt for the first megawatt. And so that's just over $3,000 per kilowatt for that first megawatt. And then it goes down half of that for the second megawatt, half of that yet again for the third megawatt. It's capped at 3 megawatts and also at $5 million per project. In the eastern United States, New Jersey has a program for fuel cells that pays about $3,000 per kilowatt. Connecticut has a program where you can lock in the renewable energy credits for 15 years. And in UI and CL&P, it's 2 different rates, but they're right around 5 or 6 cents per kilowatt hour. So if you're paying, 14 cents a kilowatt hour, and you put in a fuel cell that can generate electricity for 12 cents a kilowatt hour, and then you're able to get another 6 cents back on your renewable energy credits, at the end of the day, you're only paying 6 cents a kilowatt hour. When you combine these with the federal investment tax credit that's available through the end of 2016, which is 30%, it brings the price of these fuel cells down quite significantly. And then, my last slide on energy cost savings, it just kind of plays off what I was just talking about. In Connecticut, for instance, where baseload power is about 14 cents a kilowatt hour, we can beat that by 2 cents, and then you apply the credit. And so if you're in some place like, Texas, where you're only paying 7 cents a kilowatt hour, and we come in there and say, we can give you electricity for 12, you'd likely ask me to take a long walk off a short pier. But in states like California, Connecticut, New York, and New Jersey, where electricity prices are high and they're offering a subsidy to install one of these things, then we can oftentimes beat utility prices, and we're very comparable to some of the other generation technologies that you see on that slide, including wind and solar. So next slide. That really wraps up my presentation for now. Once again, I apologize for the glitch at the beginning of the program. I was all ready to go, and then all of a sudden my internet connection cut out. But I think we're gonna leave about 15 more minutes for questions. And so that concludes. If anybody's got any questions, there is my direct contact information. And if you're on the East Coast, I can put you in touch with some of my East Coast colleagues. If you're on the West Coast or in the Western United States, I can take your questions directly.
Okay, great. Thanks, Ken and Jim and Ernest. And we do have a number of questions to get through. I think we got enough time though, and yeah, sorry for the technical difficulties here. It happens when you're dealing with the internet, unfortunately. So we'll start off with maybe a couple of more general questions, and then get in there. There are a number of financially focused questions. We'll see if you can answer as well. So the first one is something that that Ken, you touched upon, and Jim, you mentioned as well, which is a question about using these types of fuel cells in a microgrid along with variable renewable technologies. If that's able to be an application that can be put into place based on the fact that it sounds like the fuel cells work best when they're running continuously.
I think I can take that question, but it seemed more like a statement than a question. Can you boil that down into a question?
Sure. So are fuel cells being used along with variable renewables? And if so, is there any issue in that respect?
You mean as to how they pair up with other renewables on site?
Yes. As far as, fuel cells, if they're acting, can they fill in the gaps in renewables, or are they more well-suited for baseload? I mean, it sounds like baseload, but can they
okay, so now I
gaps?
understand.
Yes.
Yeah, so they're better suited for baseload, although, they can pair up well with an energy storage project like we have out at Santa Rita Jail in Alameda County here in California. They've got a 2 megawatt energy storage project along with solar as well. And all three of those technologies, the fuel cell, the energy storage, and the solar, combine to give the jail its energy use and waste heat. So, there's plenty of projects around where we have put a fuel cell as well as solar, and it hasn't caused any problems.
Okay, great. There was a question that came in wondering about the difference between the beginning of life and end of life of a fuel cell, and what causes the any degradation that occurs over the lifetime of the fuel cell.
Yeah, so we purposely derate our fuel cell a little bit every 6 months over the course of the 5-year stack life. And so a fuel cell over the course of 5 years will degrade in electricity output about 10%. And so a 2.8 megawatt fuel cell will, be down to like 2,560 kilowatts by the end of that 5-year life, but it will increase correspondingly in waste heat. And part of the reason for that is that, these fuel cells are made up of various kinds of metals in a ceramic layer. And over the course of time, depending on how clean that fuel is coming into it, it can cause buildup on the metal. And so after about 5 years, that fuel cell stack will need to be replaced. And so by automatically derating it, we're just keeping up and making sure that the fuel cell doesn't fail catastrophically.
Okay, and in a related question, there was a question about how much of the initial cost is allocated towards replacing the stacks every 5 years.
About 1/3.
1/3. Okay, great. And as far as the cost of replacing the fuel cell itself, what percentage would that be as far as the value?
You mean at the end of the year, at the end of the contract life?
Yes.
That's going to be a question for my finance guys to answer. Once we get into the weeds of a particular deal, right? And so I think what the question is if you sign a 20-year PPA and you use that electricity for the next 20 years, can we sell that thing at the end of life? And the answer to that question and how much it's going to be is going to be a question as to I'm going to have to ask my finance guys to address that. So if whoever asked that question wants to contact me at kwicker@fce.com, I can put you in touch with the right folks and we'll get you a straight answer on that.
Great. Yeah. And so just to clarify for people here, it sounds like over the 20-year lifetime of the contract, the fuel cell does not need to be replaced, but the stacks will be replaced every 5 years.
That's correct.
Yep.
So the stacks will be replaced after initial 5 years, and we're forecasting that we'll be able to extend that to 7 years. And so we actually, into our pro forma, we'll build in a replacement stack in year 5, year 12, and year 19. And that will be incorporated into the price of the PPA so that the end user is not seeing an increase in that price, right? And so if you lock into a contract over 20 years, you're not going to pay for a new fuel cell stack every 5, 12, and 19 years. It's already incorporated into the price, as well as the maintenance agreement for all of that.
Mm-hmm. Great. So we've got a bunch of financial-related questions, and I imagine a lot of this is going to depend on the project itself, but I'll throw them out there and see what you make of them. People are wondering what is the kilowatt-hour generation cost of say a 1.4 megawatt fuel cell. I know in your slide you had 12 cents. Is that a common price level for the per kilowatt hour, or is that just a representative cost for an example project?
Well, it's a representative cost. I can tell you out here in California that electricity is usually around 11 to 12 cents a kilowatt hour. And with the SGIF and the federal investment tax credit that's put into place, on a 1.4 megawatt unit, we can produce electricity, all in for about 10.5 to 11 cents a kilowatt hour. And so it's almost an apples to apples comparison, but the advantage is that you're getting the waste heat for free above and beyond that. And then electricity prices are escalating at, anywhere from about 2.5 to 5% annually, and gas prices are only escalating at about 1 to 2% annually. And so if you're paying for natural gas to go into this fuel cell rather than buying electricity from the utility, then that lower escalation rate on natural gas is going to bring you greater savings over time.
Can you give us any estimate on what an average client ends up saving on electricity and thermal combined?
On a 1.4 megawatt unit, that all depends on how much that average customer is paying. On say you're paying 12 cents a kilowatt hour over the course of a 20-year contract with electricity escalating at 4% and gas escalating at 2%, I'm going to, say it's around $12 million.
Okay, great. And another question came in about the typical return on investment if a company were to purchase the fuel cell outright instead of going through the PPA arrangement.
Mm-hmm. I've seen paybacks as low as 5 years.
Mm-hmm. Great. So I'm going to ask you a technical question, and I don't have any idea exactly what it means, but I'll throw it out there because it was asked. So someone asked, what are the hydrogen sulfide and siloxane levels that the treatment skid can successfully treat?
That is a technical question. I believe I addressed that on slide number, I'm going back up through the slides now, and we talked about that on slide number 8. The sulfur was 10 parts per million and the siloxanes were 100 parts per million, and the total metals were less than 1 part per million.
Okay. I'll consider that answered.
Right, and if somebody wants more, if the person that asked that question wants more information, just contact me directly, and I'll put you in touch with one of our engineers, and we can have a more technical discussion about that.
Yeah, so this seems related. Have your systems ever been tested with landfill gas with a much higher level of contaminants?
No, they have not. We look for about 55% methane, and landfill gas doesn't typically have that much methane in it, and so we haven't found a landfill that was rich enough in methane to be able to test one of these. On top of that, the amount of pollutants, not necessarily pollutants, but the amount of nasty chemicals and metals that would cause fuel cells to have a problem with the gas quality are much more prevalent in landfills than they are in a wastewater treatment plant.
Yep.
That's not to say that we wouldn't do it, but one of the qualifiers is how much methane is in the gas.
Right.
And if the methane is only 20% in a landfill, then it's not worth the time. Yeah.
So this leads right into this. Wondering about what is the electrical efficiency when using a biogas as compared to straight natural gas?
So the less methane in the gas, the less efficient the fuel cell is. And so if you've got natural gas with 100% methane in it, it's going to be higher than 47%. And that 47% is a fleet-wide average of electrical efficiency, right? And so if you've got something that's got, 50% methane, then the electrical efficiency might be lower, say 44, 45%.
Mm-hmm. So let's see what else we got here. Questions keep coming in. So can you speak to the role that utilities have to be involved in setting up a fuel cell project like this?
Can I speak to the role that utilities have to have? Well, we need an interconnection agreement, obviously, and we'll take care of that on our side. Out here in California, you know, there are air quality management districts that you don't need to get a permit with because we're not burning any type of fuel and we're not putting any we're not putting any large amounts of particulate matter or NOx or SOx into the atmosphere, and so you don't have to get an air quality management district permit, but you need to get an interconnection agreement with the utility, and that usually takes 6 months or so. We typically say that from signature of a PPA or a purchase or a lease, it takes about a year to get one of these things installed. And so right now, the federal investment tax credit is funded through the end of 2016, which means that if you've got a fuel cell project up and running, by the end of 2016, you'll be able to capture that 30% investment tax credit. And so now is the time that if somebody's interested in getting one of these fuel cells, then we should move forward in discussing it soon, because it usually takes a month or two once somebody expresses interest to go through all the presentations and negotiations to get a contract in place. So really, we're at Q3 right now, and soon to be Q4. And you know, if somebody waits until next March to sign an agreement, we can't guarantee that that investment tax credit will still be in place by the time we finish.
Sure. So would you say for the interconnection with the utilities that is that process fairly standardized at this point, or is it still kind of it is?
No,
okay.
It's pretty standardized.
Great. Well, we are just about out of time. Some questions rolled in at the end that we did not have get a chance to address, I'm afraid. But you know, reach out to Ken and Ernest and Jim with any questions that you may have, and I'm sure they'll be happy to answer them. Do you guys have any final thoughts that you'd like to leave us with?
I certainly appreciate everybody's time, and once again, I apologize for the glitch. And if anybody's got any questions, certainly reach out to me directly, and I'll get to it either this afternoon or tomorrow morning.
Great. Sam, anything you'd like to leave us with as far as getting these things up online?
Sure. Well, a recording of this webinar should be up online within 24 hours, and we'll also post slides of this webinar, and that will be posted on our website. You can go to resilient-power.org. And a couple other notes: if you're interested in our newsletter, if you don't already receive that, you can read archives on our website, or you can sign up at the link on your screen. And we also have a few other webinars coming up in the next month. We have one on Monday. The Oregon Department of Energy has issued an energy storage RFP. We'll be talking about that on Monday. Then we have our first in a series of energy storage market updates at the end of the month, and another fuel cell webinar coming up in October. And I think that's it for today. Here, this is our contact info on the screen. And thank you, everyone, for joining us and for bearing with us during the technical difficulties.